Today I would like to talk to you about two technologies that the Central Glass and Ceramics Research Institute, situated in Kolkata, which is part of the Council for Scientific and Industrial Research in the country, has brought out in the recent past. As you know, fiber laser technology has grown and made dramatic progress in the last few years. We at Csir-Cgcri have developed the technology and by taking up very comprehensive program and developed packaged fiber laser systems, both at 1 micron and 2 microns, and these are now available for commercial applications. And what we have done here is we have started the laboratory development of rare earth doped fiber materials in the laboratory, and the project was taken up in the 12th 5-year plan of CSIR, and today we have a state of the art facility set up for this purpose. We have been able to demonstrate this on a first time basis globally, which is basically the vapor phase doping technique, and the reliability of this has been extremely high. We have developed the double clad fibers which are suitable for high performance applications, and this could then be designed, can be used for all fiber lasers at both 1 micron and 2 microns. The aim further will be to build on this indigenous capability and making packaged laser systems starting from fiber stage onwards for both industrial and medical applications, and thereby Csir will build on the capability and close a gap that exists today in the country. The second technology that we have taken up is development of a supercontinuum broadband light source, and made by using non-linear photonic crystal fiber, and this has been developed under the CSIR New Millennium Indian Technology Leadership Initiatives. And using the supercontinuum broadband light source, fiber light source developed at Csir, we have made a confocal microscope. Today, depending on this development, the company has received more than 12 commercial orders, and this particular facility will be of great use to our scientists, especially in the life science area. And our system now consists of an excitation pulse pump laser, laser drivers, power stabilization circuits, and photonic crystal fiber, and also the required collimating optics and power supply. It is packaged inside a box, and this light source is then works on a 24 volt supply, and it is developed along with this company with a RS-232 interface, and the product will be have multiple applications in the area of biophotonics, where broadband sources as a supercontinuum can be used for experimental purposes. This allows you a new way of broad spectrum spectral and illumination sources, and the technique and the technology we have developed in making the supercontinuum broadband light source will now get into a large number of applications in the area of communications, and also soon will have its impact in defense technologies. Thank you.
Csir-Cgcri has a state-of-the-art MCVD system for vapor phase deposition of rare earth and aluminium to fabricate active and passive fiber preforms. Diligent study since 2010 has resulted in optimized process parameters yielding reproducibility greater than 90%, which has not been achieved by any other MCVD process till date. Active fiber preforms with diameter greater than 4.5 mm and aluminium concentration up to 17.8 mole% have been demonstrated. Preforms of various designs have been achieved devoid of central dip and core-clad interface defects. Using this facility, Csir-Cgcri has successfully demonstrated large core active fibers with uniform dopant concentration and low photo darkening effect for the first time. An output power of 100 watt at 1.06 micron has been achieved. After the preform has been fabricated, the uniformity of refractive index is measured using a preform analyzer. Specialty fibers such as pentagonal, hexagonal and double D as well as multi-core fibers can be drawn in a single tar. Low refractive index as well as high refractive index coated fibers of different designs can be drawn using this facility. Fiber capillaries can be drawn in another tar with a precision of 20 micron. Photonic crystal fibers are fabricated by stack and draw method. Highly nonlinear photonic crystal fibers are fabricated which have application in supercontinuum generation. Hollow core photonic crystal fibers are useful for beam delivery as well as sensing applications. Subsequent to fiber drawing, fiber refractive index profile as well as the fiber geometry is measured using the fiber analyzer. Csir-Cgcri has the facility of lifetime measurements for silver doped, bismuth doped and rare earth doped fibers. The fiber transmission characteristics can be measured in a wavelength range between 0.4 to 5 micron. Subsequently, the fiber loss can be calculated in this range by the cutback method. State-of-the-art fiber laser facility for designing and prototyping of high-power fiber lasers at both 1 micron and 2 micron wavelengths have been set up. In the past few years, knowledge of continuous wave as well as pulsed fiber lasers has been acquired and implemented towards both basic and application-oriented research. The laboratory houses many advanced facilities for the development of CW and pulsed fiber lasers. Time domain, spectral domain as well as spatial beam profile measurements are possible with the available facilities which are useful for the laser prototype development. Aiming towards metal cutting, marking and engraving applications, both continuous wave and pulsed ytterbium fiber laser at 1 micron have been successfully demonstrated. So far in the 1 micron regime, 20 watt of continuous wave laser power and 10 watt of pulsed laser power with up to 8 kilowatt peak power have been demonstrated with different pulse widths and repetition rates in packaged form. Further scaling of power is in progress. In the 2 micron regime, development of both continuous wave and quasi-continuous wave laser has been directed towards medical applications such as soft tissue surgery. Diode pumped high-power thulium-doped double-clad fiber laser has been configured, delivering more than 5 watt of CW power at 1.95 micron, and further scaling of power is in progress. Quasi-continuous wave fiber laser, which can deliver high energy in comparatively long duration pulses, is also demonstrated with watt level average power. In a tabletop setup, launching a narrow ultra-fast pulse into an in-house fabricated nonlinear photonic crystal fiber resulted in a supercontinuum in the range of 400 to 2400 nanometer with a high power density. The supercontinuum source can be used for optical coherence tomography as well as imaging.